Okay, well, we're going to answer these questions for our physiology exam. This is Unit 3 over the cardiac cells, and this is going to be awesome. Welcome. So right now we're going to talk about the autorhythmic cells here, and then we're going to talk about cardiomyocyte cells. These are action potentials and ion flow, and then we're going to talk a little bit about EKGs, which is going to be sweet. So for starters here, we're going to start here and we're going to talk about the autorhythmic cells. So autorhythmic cells are going to have three phases. Our first phase is going to start below our line of threshold, and it's going to be called we call phase 4. And we're going to have this gentle uptick here, and then we're going to have this spike, and then we're going to have this slowly decreasing down to where we started, and then we'll repeat the slow uptick to threshold, the spike, slowly decreasing down to where we start again. So now let's talk about what all each of these phases are. So we have phase 4 here. Phase 4, we're going to talk about funny channels. Funny channels are kind of strange. They're only found on autorhythmic cells. And so what we're going to be doing with these funny cells is these funny channels are these channels, we'll write it right here, IF, funny. Funny channels can be stimulated by hyperpolarization. So as we can see here, this whole phase is in hyperpolarization underneath threshold as it's below threshold. And so what will happen is this will stimulate the IF channels to open and let in some sodium. Another thing that can stimulate them is beta receptors, which will increase CAMP, which will open up these channels as well. So as these channels open, we see that there is a slow uptick in sodium in the cell, and eventually the cell will reach threshold. When the cell reaches threshold, then we have phase then we have phase 0. In phase 0, we get the opening of calcium channels. And so these calcium channels will open here, IF, or sorry, not F, I calcium. And it will release calcium into the cell, which will stimulate calcium to be released from the smooth or the SER. This will cause rapid depolarization of the cell. As we can see in our chart here, we've got this rapid depolarization. And there are also long-lasting and transient, so we have L-type and T-type channels. And because these take a second to close, they're going to stay open for a second. They take a minute to close. That's why we have this plateau. Not necessarily a plateau, but this longer, it's not a sharp peak like this. And what happens is as we reach this point, the driving force between potassium gets really high. And then we have these potassium channels that now want to let in potassium into the cell, which will be stage 3. So I'll label these really quick for you. And this is going to be right here. If we look at our action potential, potassium coming into the cell. And so we first have these funny channels opening, allowing for the slow depolarization. Then we have rapid depolarization as calcium channels open. The long-lasting calcium channels take a second to close. Once they close, then we get potassium channels. which will hyperpolarize the cell, which then open funny channels again, and our process repeats. And that is how they work. Keeping in mind at all times, as long as there's oxygen, we have our sodium potassium pump functioning that's pushing out sodium and pulling in potassium into the cell. This is always going on in the background. Now we have our cardiomyocyte. In our cardiomyocyte, what's happening here is we have a few autorhythmic cells in our hearts that are starting action potentials. Because we can have these funny channels that will function with very little stimulus, they're going to keep the heart beating at a pretty consistent rate, and they don't need a stimulus aside from hyperpolarization or CAMP in order to start. Whereas here in our cardiomyocytes, we need an initial stimulus to start our action potential. So if we start on our action potential chart, we'll start down here. We're looking around negative 90 resting membrane potential, because that's the nurse potential for potassium. So we're going to have these potassium ionic rectifier channels that are open at rest. So we have a lot of potassium in the cell that's keeping the membrane potential low. What happens is, if you think, here we have a autorhythmic cell next to this cardiomyocyte. What will happen is, as we have this increase in these positives in our autorhythmic cell, they're going to spread through gap junction into the cell next door. And as they spread into the next door, they're going to cause action potential. So here, we have our step 4 as we look at our action potential chart. And in our step 4, we're going to be having this influx of potassium. So influx of potassium keeping the rest of the membrane potential low. But as we have our influx of this Buang into the cell, then we're going to have sodium channels that are going to open, causing a large influx of sodium into the cell, which is going to cause a rapid depolarization, which is going to be step 0. So we have some sodium channels that are opening, applying for rapid depolarization. Here at step 1, at the peak, then we're going to have the opening of some transient potassium and also these transient chlorine channels into the cell. And we're going to put them right here. We got these transient potassium and chlorine. It's going to allow for a little bit of rapid hyperpolarization again. But then at this point, we're going to have, so I'll label this as 0. I'll label this as 1. And then here at step 2, we're going to have a lot of things occurring. This Buang, it's spreading to these sodium channels. It's also going to come over here to this calcium channel. And we also have transient and long-lasting channels here. And this takes a second to open. These calcium channels are not super fast at opening. And so, but once they open, they're going to open up, which will keep our cell from hyperpolarizing too quickly. At the same time, we're going to get opening of some potassium channels slowly. So at this point, we have calcium channels open. And also at that same time, we're also opening up a potassium ultra rapid channel. And then soon thereafter, we're going to open up a potassium rapid channel. And then after that, we're going to open up a potassium slow channel. And because we have these calcium channels open and at the same time as all these potassium channels, we're going to get a plateau. This plateau is, we have this action potential that keeps kind of this steady pace. It's not hyperpolarizing very quickly, It's also not depolarizing. Get a plateau. But then we'll reach a point, so this is step 2. Then we'll reach a point where we'll have a rapid depolarization, because here in step 3, we have our ion rectifier potassium channels opening, which get bigger and bigger and open more and more, which lead to more potassium coming to the cell. We get step 3 here, and it's also step 4, as it's coming into the cell faster and faster. And this is going to rapidly hyperpolarize, and it's also going to cause the resting membrane potential to stay where it's at, leading to another step 4 here, similar to where it was over here to start. And this is how cardiomyocytes function. And so, with remembering, we let in calcium during step 2, which also will release calcium from the smooth endoplasmic reticulum. And also remember that we have this sodium potassium ATPase always going on in the background as well. Those are important things to remember. And so, as we see, when the autorhythmic cell occurs, when it depolarizes, it's going to send up Wong, which is going to spread, and it's going to cause an action potential in these cardiomyocyte, which is going to spread to the next cell over and cause an action potential in the next one, which then spreads to the rest of the heart. Now, if we go down to our EKG, as we can, if we kind of think about what's happening in the cell, if we say this is one of our autorhythmic cells, what's happening here is we have this action potential that starts, and it's going to spread to the whole cell. The whole heart is going to spread, and it's going to depolarize, leading to contraction. Now, as we look at EKGs measure the charge outside of cell. Outside of cell. And they're going to track what's occurring with the electrical signals in the cell. And so we're going to get what we call, I'm just going to write this here. We're going to have, on our EKG, we're going to have a P wave, then we're going to have a Q wave, an R wave, an S wave, and then we're going to have another, what we call the T wave here. So this is the P, Q, R, S, T wave. And that is going to be what we're going to track here. So for starters, the signal occurs first here in the SA node, which is in the atria. This signal is going to have, it's going to depolarize and send these negative signals, because if it's tracking the outside of cells, if typically we have a more negative inside of cell and more positive outside, as we get positive charges coming into the cell depolarizing, suddenly the inside of the cell is going to be positive and the outside is going to be negative. And as this spreads, we'll have more negatives on the outside of the cell spreading. And so as EKGs check the charge on the outside of the cells, we're going to watch as these negatives spread throughout the heart. And so I'll erase this so we can get some space here. As we track this on the EKG, as we have this charge starting at the SA node, and we have this spreading throughout the heart of these negative signals, these negative vectors are spreading towards a positive sensor here. And so as they do that, they're going to cause a change in our EKG. The general rule is a negative vector towards a positive receptor will cause an uptick in the EKG. And the opposite is also true, obviously. And so as we see here, as we get these signals being sent towards these negative signals, we have negative signals being sent towards a positive receptor. On our EKG, we're going to track a small uptick. And as this spreads to the whole atrium, to both sides, and it fills this atrium, we're going to see this uptick increase, and then as we depolarize the entire atrium, it's going to finish, and then we have our P wave here. As we come down to the next step, thinking this entire area is already depolarized, we're going to have depolarization of our ventricles, but it's going to start from this little section right here, and the initial movement is going to be to the left, as we're showing here. And this is going to actually cause, if you draw a line between these receptors, you can kind of see that the net vector is going towards the negative receptor. So we have a negative vector going towards a negative receptor. That means we're going to go down our EKG. So if we have our P wave from our last section, then we have our drop. This is our Q wave. We can see this is occurring because the net vector is going negative. But very quickly, as we depolarize this whole area here, we see our net vector switches quickly down to the rest of the ventricle. And now we have this rapid increase, which is our R wave. As this whole section gets filled in, and all this occurs and gets depolarized, until we have this section right here on the heart, which still needs to be, and this is our superolateral section of the heart that depolarizes last in this section. And because we have this movement upwards as we depolarize, the net movement is actually towards our negative sensor. So we have a net movement towards our negative, so we have a negative movement towards a negative sensor, which means we're going to go down. Once we go down and drop below our normal position, this will be our S wave. And now if we track our last section here, we have our P wave, our Q wave, our R wave, and we have our S wave. Now, if we think the entire heart is now depolarized, we need to repolarize the heart and get it back to normal. And so as we do this, what we're going to be doing is we want to think we're going to repolarize from epi to endo. Meaning we're going to start here on the outside of the cell, outside of the heart, and we're going to move in. And so initially we have this strong net force that's going this direction, which is going to cause an increase here in our signal on the EKG, and it's going to just continue, and it's going to continue to go, which will lead to a greater increase in our EKG, upward tick, and then as it fills in, there's a less net force as it gets more depolarized or repolarized, and it's going to continue back down. And as I draw this in black really quick, then we get this little upward tick, which is going to be, this will be our T wave. And so that is how we get our atrial depolarization, our ventricle depolarization, and our repolarization. This whole section is what we call the EKG. That is what happens in the heart as we do an EKG, and this is what happens in the heart as we are working with autorhythmic cells and cardiomyocytes and action potentials. Thanks.